Welcome to an introduction to the theory behind IR spectroscopy. We're going to see that IR spectroscopy takes advantage of a quantum regime that involves vibrational quantum levels. We'll recall that UV spectroscopy is actually the promotion of electrons from one electronic energy level to another. So you're moving from one orbital of a certain energy to another orbital of a certain energy. But in IR spectroscopy, we are dealing with the spaces between those lines, the vibrational quantum energy levels. So this is what we're going to be talking about. We're going to start off with sort of an overview of the theoretical model that we use to develop the math. We will describe the quantum nature of that model. We'll use that model, or the simplified version of the model, the harmonic oscillator, to calculate the frequency of a representative carbon-hydrogen bond. And then we'll see if those calculations give us an answer that relates to experimental data, thus validating our very poor analogy for the truth that is our model. So here is sort of the simple model. The simple model involves basically a parabola called the harmonic oscillator. And that involves the idea that if you have a carbon-hydrogen bond, it has a preferred bond distance. But that's not static. When someone says the carbon-hydrogen bond is a certain value, what they mean is that that is the average bond distance for that system. It actually vibrates because a bond is really an electric field in which electrons move, and just like anything in a magnetic field, you can move in and out of the potential well of minimum energy. So this hydrogen can vibrate back and forth relative to the carbon, and you can have a longer stretched bond length and a shorter compressed bond length. Just like a spring. Any spring you have, when it vibrates, is getting a little shorter and a little longer. And we can model this on this idealized perfect spring model. So as you stretch this system, as you stretch it farther and farther and farther, what you're getting is from the perfect bond distance, the bottom end of that energy level, you're rocking back and forth in this potential energy well. So you go from the compressed distance to maybe the stretch distance, and you see basically if we go up in energy, we will stop and then roll back down and come back up, and we will stop, and we're just rocking back and forth in that energy well. And that is going from compressed to stretch with the bond distance. Notice, of course, that if we stretch it more and more, we just get to higher and higher energy. And if we should stretch it to infinite distance, we're just at infinite energy. And we know that makes no sense. If you stretch a carbon and a hydrogen bond more than a little bit, you basically have a separate carbon and a separate hydrogen. You know, if you have a pen on you right now that's got the little clicky top, take the spring out and stretch that spring a little bit and watch it go right back to where it was. Now stretch that spring a lot and see what happens to it. Well, a model that describes what happened to that spring you just wrecked is the Morse potential, because it imagines these possibilities. It imagines that you can break the bond, and it imagines that there is a distance that is cannot be surpassed when you get them too close together, because basically unless you're going to do nuclear fusion, the nuclei cannot touch. So once you get close enough that the nuclei start to repel each other electrostatically, your energy is going to go through the roof. And as you get farther apart, there'll come a point where suddenly the energy doesn't change anymore, because there's no difference between a carbon and a hydrogen atom 1 foot apart and 1 mile apart. They don't even know each other exists. Why would the energy be any different? So basically you can go too far. I know what you did with your slinky last Christmas. You went too far. And the same thing can happen with real bonds and real springs. Now, the mathematical model that describes this is called the Morse potential, and it has the exact same ideas. You can have a spring slightly compressed, you can have the spring slightly stretched, but it imagines the possibility of the fact that you cannot go past the minimum internuclear distance. There's a point at which the nuclei get too close, you basically reach a ridiculous amount of energy. There is a line you cannot cross. So rather than it being a parabola, and a parabola just opens up forever, if x gets to infinity, the parabola is infinite wide at the top. But this is asymptotic. It implies there's a line we can't cross. So there's some place we can't get any smaller than. And there's another place that we can't really change the energy anymore. Once we've stretched that bond enough, the energy is the same. A broken bond is a broken bond. There's no difference in energy. So the Morse potential looks just exactly like the dissociation energy profile for a bond. I mean, this is basically a bond's energy profile. It vibrates, it can be broken, it can't get too close together. Why do we use the harmonic oscillator when the Morse potential would be far more accurate? Well, the answer is this. The math of the harmonic oscillator is very simple. It's based on Hooke's law, and well, basically it is Hooke's law. It's Hooke's law applied to a rotating oscillating system. And so that's very simple math. The math of the harmonic oscillator is a lot more complicated. And truth be told, you will be using that math if you're doing advanced theoretical calculations on transitions of vibrational levels in the upper vibrational levels. You'll have to use the Morse potential. But you know what? We're working at room temperature here, not 1,000 degrees. So virtually all of the molecules that we're talking about will be in the bottom of that well, right at the bottom energy-wise. And notice how they look almost the same at the bottom. So because they're very similar at the bottom, we could use the same math for both, and just as long as we're not talking about getting too hot, as long as we're not talking about getting into upper levels of vibrational energy, stick to the bottom, the very first transition, and our math should be almost identical. That's nice to know. Now let's talk about the quantum nature of this, because this isn't a ball smoothly rocking back and forth across a potential energy well like we see in the macroscopic world. This is a single bond in a single molecule having to fit its vibrations into a very specific and limited vibrational or energy regime, so there's only certain energies that can be stable, or certainly certain energies that exist. So with the harmonic oscillator model, what's observed is that we can see that there are vibrational energy levels which have been labeled 0, 1, 2, and 3. So vibrational energy level 0 is the bottom one, and their energy starts off at 1/2. It's proportional to 1/2 the frequency, then 3/2, then 5/2. So you can see basically it's 1/2 plus n times Planck's constant, which is Planck's constant just converts the frequency of a photon to the energy of a photon. So 1/2 times Planck's constant times the frequency of the vibration that's observed, and we'll have the energy of this level. And then we go up a whole unit here. Notice the difference between 1/2 and 3/2 is a whole unit. So we're going up by an HV unit every single time. Planck's constant times frequency unit every single time. I guess it's not V, it's actually nu, but I don't know my Latin very well. So there's the energy levels. So if it's vibrational energy level 0, the energy is 1/2 Planck's constant times the frequency. Now, that implies, right there, that implies the idea that there's an intrinsic energy in your molecule, that there's this 0-point energy. And you'll hear a lot of quacks out there saying 0-point energy, we can run the world on 0-point energy. Well, if you ever got that energy out of your molecule, you're basically, I don't know what happens to it, but it's not going to be a molecule anymore if you ever were able to extract that energy, I don't think. So why is there a 0-point energy? Why is it that no matter how cold a molecule is, its bonds are always vibrating? Well, as we will see, the answer to that lies in the uncertainty principle. So even the lowest vibration energy level has vibration. When we convert from one energy level to another, we only go up one at a time in the harmonic oscillator model. Because of its symmetry, because of its pure perfection, the math basically forbids a double transition. We just can't do a double transition. But you know what? We see them all the time. And why do we see them all the time? Because the reality is the Morse potential, which is asymmetric and does not completely forbid two energy level jumps. Now, they're much less likely, because remember, toward the bottom of the energy well, the shape is very similar to the harmonic oscillator. So really, as you may have already perhaps gathered in the world of chemistry, forbidden doesn't mean impossible. It just means really, really unlikely, because nothing's perfect. So the difference in energy level between any pair of, or the difference in energy between any pair of energy levels is basically equal to HV, or H times frequency. So that transition is going to give you the energy between those two levels. Now, in the Morse potential, we can have that double transition because of the asymmetric energy profile. The other thing I want to point out in the Morse potential is that each energy level is a little closer to each other. And of course, you might expect that when we get to the point where we're breaking the bond, those energy levels sort of get infinitely close together. I'm no quantum chemist, but I just look at this and I wonder if the area here in this section here, if I was to cut that out and weigh it, if it would weigh the same as this area. Because as the system gets wider, the lines get closer together. I wonder if that turns out to be true. If you ever get a chance to do that math, do it and let me know. I'd love to know. Now, as I said, because of the asymmetry, a jump of 2 energy levels is not out of the question. But one thing you'll notice is it's not going to be twice. Right? We are going from an energy level here to here, it's a certain value, here to here, it's a little less than twice. And we'll see that when we see harmonics, which are these double energy jumps in IR spectroscopy, they will not be twice the frequency of the base peak. They'll be just a little less than twice the frequency of the base peak, and that's why. So let's look at sort of what these things look like in the quantum level. We are aware that quantum energy is actually a wave function. Well, here's our harmonic oscillator. There's our vibrating bond, and if that bond's vibrating, there's a certain probability it'll be at any place. So the wave function describes the probability of that hydrogen being in a particular place. And there's the wave function, or the probability function, it's the square of the wave function, for a single bond. And it just describes a probability. The hydrogen's most likely at the center, but it could be at either point. Now, what is the next energy level up look like? Welcome to quantum craziness. So the probability of the next energy level up, this molecular or quantum molecular orbital formula resembles a p orbital. It looks just like a p orbital. And so when you square it, there's 2 lobes of probability, just like a p orbital. Isn't that kind of wacky? So in the next quantum level energy up, it's not like that bond is vibrating just like faster. It's actually just changed its probability to be in 2 separate places. But you'll also notice that the probability describes a wider track. So really, you could think of it as this bond is moving farther now. But really what's happening is the sort of the, making a graph that describes 95% of its possible movement describes a wider area than a graph that describes 95% of the possible movement of this particular wave function. And as we go up in wave functions, they just follow that, just increase the number of nodes, just like as if you were adding p orbitals in a pi system. So more and more nodes, more and more nodes, more and more nodes. And you'll notice, much like pi systems, the outside lobes have a bigger coefficient than the inside lobe. So we're starting to see this sort of peak toward the outside as we get to higher and higher energy levels. And what does that move to sort of at the infinite extreme? It looks a bit like this. Once you reach sort of really high energy levels, it looks exactly like the probability function you would get with a swinging pendulum. Remember, swinging pendulums go slower at the edge. Then they swing through the middle quickly and go slow at the edge. So if you were asking yourself where you'd find that atom, it's going to be likely toward the edges of its bond vibration rather than dead center at the highest energy levels. That's kind of a neat thing that comes out of quantum chemistry and makes quantum chemistry look just like classical physics once we get into high enough energy level regimes or with enough particles. The quantum craziness always collapses to what we observe once things enter the macroscopic level. But on individual molecules, which is what we're talking about when we talk about spectroscopy, that light is talking to an individual molecule. It's not talking to the material as a whole. We are governed by this regime here, and we're mostly looking at the energy transition between here and here, level 0 and level 1. So that's sort of the quantum consequences. Well, now that we know how to calculate the energy of this system, we know Hooke's law, and we know what the energy is. It's n plus 1/2 times Planck's constant times the frequency. We can actually calculate the frequency. So we've got a harmonic oscillator. We know the energy that we're looking for. That's the transition. Just any one notch is Planck's constant times the frequency. We know the frequency. How do we calculate this energy right here, or the frequency that relates to that energy right there? Well, what we need is the frequency of this bond, or the base frequency of this bond. And that's going to relate to, remember, the energy levels were 1/2 plus n times Planck's constant times frequency. So if you know this base frequency and we know the energy level difference, which is always this chunk, since the energy level difference is always the same, we'll be able to determine the energy difference. Now, frequency is expressed right there in per second. That's what frequency is. How many times per second does something happen? That's frequency. But you know, how do we get that? we're going to use the assumption that it's a cyclic system, and it is. It's rocking back and forth. This 1 over 2 pi here is related to the fact that it's a cyclic system. It's related to the force constant of the bond. This is Hooke's law here. This is Hooke's law for a spring. Hooke was a great scientist. He was involved in rebuilding London after the Great Fire. If memory serves me correctly, he was one of the architects of St. Paul's Cathedral in London. So, you know, big important guy. And he came up with this law for the physical motion of a spring. The force constant for the spring, which is how strong the spring is. And the stronger the spring, the higher the frequency. So that seems to make sense. The bigger that number, the bigger the frequency is going to be. Divided by the mass of the object that's being vibrated. Now that's all fine if your spring is connected to the wall of St. Paul's Cathedral. Only the mass of the object you are operating is moving. But that's not true in molecules. Both objects are moving. For example, if you were to hold up a giant cinder block and vibrate it back and forth, I guarantee you the cinder block's moving, but so are you around your mutual center of gravity. So as a result, both of your masses are involved. So we use a term called reduced mass. Reduced mass is the effective mass change around that center of gravity. And so it's basically both mass multiplied together divided by both masses added together. That is the reduced mass. And if you look at it closely, you'll see that the units are going to be in mass units. So basically, unit times unit, that's unit squared. Units plus units, that's still units. Unit squared divided by units is going to give you units. So grams squared divided by grams will give you grams. So reduced mass is mass. It's just a mass that sort of combines both. Now, in IR spectroscopy, we don't talk about frequencies as in per second. We talk about frequencies as in the number of oscillation in a centimeter. So we talk about frequencies related to distance. And we do that so that we get a directly proportional relationship between energy and the bond vibration. So the conversion is easy. You're just using the speed of light because we know that it moves so fast and we know that it oscillated so many times. So we know how many times it oscillated in a distance. Basically, you take the frequency, you divide by the speed of light, you're going to get the wave number, which is the number of waves in a distance. We're using centimeters, so the speed of light must be in centimeters. Why centimeters? I don't know, but I do know that astronomers love the unit centimeters. So I would suspect that this comes out of astronomy in the very early days. When they talked about frequency, they talked about it in per centimeter. So here's the formula for the wave number for a bond vibration. All we did was divide the frequency by the speed of light. So here it is. There's the entire formula divided by the speed of light. So that's all we did. Now, let's look at the frequency for a particular molecule. If we wanted to sort of calculate what that is, we need to know the force constant. We need to know the masses involved. We know the speed of light. Everyone knows what pi is. It's so tasty. We all know what that is. So there's our formula. The reduced mass is going to end up being in grams. The mass of most atoms in any table is in grams per mole, not grams. We need grams, not grams per mole. You're going to get wacky numbers if you use grams per mole. So the reduced mass can't be in grams per mole. How do we solve that? Avogadro's number. So we're converting grams per mole into grams. So we can use the numbers from the periodic table. Carbon, 12 grams per mole. We can use that as long as we divide our final answer by Avogadro's number. If we collect all those constants, Avogadro's numbers, 2 pi and c, those are constants. They're never going to change. So we can turn them into a final number right now. 4.12 is that number. So now we have a formula for the vibrational frequency in wave numbers of any particular vibration. We need to know the force constant, we need to know the reduced mass, otherwise we're multiplying by 4.12. So the reduced mass for any pair of atoms is not going to change because carbon and hydrogen, their masses don't change, but the electronics might change. So in different molecules, there would be different electron densities in certain carbon-hydrogen bonds. There'd be different electron densities in certain carbon-carbon bonds, but of course the masses of those two carbons aren't changing. So this force constant is going to change with the nature of the bond, and that changes with the nature of the functional group and where it is in the molecule and what's next to it. So this is why we can use IR spectroscopy to interpret structure. We can actually see slight differences in frequency within the same kind of bonds. Of course, we see big difference in frequencies if the atoms have changed. And so we can actually find functional groups, and we can see if they're a little different and what environment they're in to a limited extent. So let's see if we can calculate the frequencies of stretching in this molecule right here. Can you name it? I'll leave you to do that. That's a skill you should be able to do right now. It's got alkenes and it has alkanes, and we're just going to look at the CH bonds right now. There's also the carbon-carbon double bond, and there is, no, I guess that's it for this. There's the carbon-carbon double bond, there's the carbon-hydrogen single bond that's attached to that double bond. That's different in nature than the carbon-hydrogen bonds that are attached to sp3 hybridized carbons. We need to know, well, we know the speed of light, we know pi, we know the masses of the elements. We just need to know the force constants. And you know what? There's some sort of ballpark figures. A single bond is about 5 times 10 to the 5 dynes per centimeter. And dyne is a unit of force. So that's just a lot like Newton meters, or newtons per meter, right? It's like how much force does it take to move it a certain distance? Well, it takes 5 times 10 to the 5 dynes to move it 1 centimeter. That's what this number here means. Why dynes? What is a dyne? Well, a dyne is an SI unit of force, and it uses centimeters, and it uses grams, and it uses all the units that we're using in our calculation. So that's why we use dynes. Its units are centimeters and grams and things that will cancel out what we're doing. If you want to use newtons, you're going to be having to convert your final answer. That's fine too. We all have calculators. So let's do the calculation. So here's the frequency of the bond. The reduced mass of a carbon and hydrogen bond turns out to be pretty close to 1. That's pretty close to the mass of the hydrogen. And if you think about it, look at this. Basically, 12 times 1 is 12. 12 plus 1 is 13. It's 12/13ths. So if we've got a big atom and a little atom, the reduced mass pretty much ends up being the same as the mass of the little atom. That's something to remember. The smaller mass will dominate the vibrational frequency. And if you think about it, you know, if this mass was 10,000 and this mass was 1, this would be the number 1. And the only thing that matters is what's moving. So basically, the smaller thing is what's moving more, and the reduced mass is all about the mutual motion. What's moving more gets more of the calculation. We know a force constant for a single bond. We put it all into our frequency here, and look what we get. 3,000 oscillations per centimeter. And if we were looking at an actual IR spectrum, we would see a number pretty close to that. For the carbon-carbon double bond, we have 10 times 10 to the 5, not 5 times 10 to the 5, 10 times 10 to the 5. But the reduced mass for a carbon-carbon bond is 6. Why is that? Because 12 times 12 divided by 12 plus 12, which of course is 2 times 12. The 12s cancel out, and you basically get 12 divided by 2. So that's 6. Do the math, you'll see that a carbon-carbon bond reduced mass is 6 grams. And so here's our frequency for a carbon-carbon double bond. So try that math. Do you get the same answer? Can you write out dynes in its SI units? Can you make everything cancel? Even underneath that square root? Can you make everything cancel even underneath that square root? Try it and see. It's a useful exercise, and it will sharpen up your math skills. All right, so is this right? Does it even relate to reality in the slightest way? Well, let's take a spectrum of our compound. And right there, I've given you the name. I hope you were able to name it 1,9 decadiene. It's a decane, but it's got enes in it, so it's an ene. There's 2 of them. It's a diene. They're in the 1 and 9 position. It's a decadiene. All right. Can we find some frequencies that relate to the carbon-hydrogen frequencies the carbon-hydrogen frequencies we just talked about and the carbon-carbon frequencies we just talked about? Well, let's see. That is the number there for 3,000, and it's right in the middle of the forest peaks that relate to CH stretches. Right away, you'll notice that there's a lot of peaks just under, and a lot of peaks just over. The force constant for CH-sp3 stretching is slightly lower than the force constant for CH-sp2 stretching. If we see peaks above 3,000, we generally say, those are on double bonds or triple bonds. If we see peaks just under 3,000, we tend to say that's just boring alkane peaks. But they're all pretty close to what we'd expect given that force constant that we were given. Obviously, all these bonds have slightly different force constants. There's many bonds here, and the molecule is symmetrical, but there's 1, 2, 3, 4, 5, 6, 7, 8 different kinds of bonds, 3 different kinds of alkene bonds, so they're kind of on the upper side here, and 5 different kinds of alkane bonds, and they're on the lower side here. That's why this is a forest of peaks. And here's the carbon-carbon stretch. This pink line here is our calculation. There's the actual result. Hey, we hit that pretty close on the nail, didn't we? So our calculations gave us the right answer. And of course they would. Where do you think we got those force constants from? Those force constants are actually from IR data. So really all we did was recalculate back to the number we should have got anyway. But if you know the force constant, you'll be able to calculate the frequency. And you see just from this how the frequency is related to the force constant and the atoms involved. Really light atoms tend to be up here. Carbon-hydrogen frequencies, oxygen-hydrogen frequencies, they're all up here. Double bonds tend to be in here. Carbon-carbon, carbon-oxygen bonds tend to be in this regime. Carbon-carbon single bonds, that doesn't have as high of a force constant, they tend to be down here. Carbon-oxygen single bonds happen to be down here too. 1200 is a pretty typical frequency for a carbon-oxygen single bond. That shows up really nicely. Triple bonds would come out, between carbon and carbon, would come out above where the double bond is, and they tend to come out in here. They're always easy to spot because this region, generally because there's not too many triple bonds in the universe, this region's pretty clear. Remember, heavy atom, light atom, single bonds, heavy atom, single bonds, increase the force constant, heavy atom, double bonds. And then this region, since triple bonds hardly ever are in your molecule, is generally pretty clear. Down here we got bending, overtones, all kinds of combinations. Matter of fact, really below 1500 on down is a region we often call the fingerprint region. It's so hairy and messy that it's basically difficult to interpret a lot of the time. But we'll concentrate on the strongest peaks, and we'll always be able to, I think, understand what's going on. So that is basically an overview of the theory of IR spectroscopy. We can use the quantum model to determine what the energy equation was. Using that, based on the frequency, which we got from Hooke's law, we were able to determine the frequency for the vibration of any one of these bonds. And now that we know the frequency, basically that'll be the same frequency as light that initiates that transition, because the frequency will be the same as the frequency of the photon. So basically we're able to understand why we see carbon-carbon double bond peaks around 1660, 1680, 1690, and we see carbon-hydrogen peaks here around 3000. This one here is probably 1650. That's pretty typical for a sort of a regular boring carbon-carbon double bond. And there's some references and confessions for you. I hope you enjoyed learning about IR theory.